So we are going to keep making things just a little bit more complicated. I wouldn't say complicated, but more realistic, let's say. Okay. So now we move to a vertical profile of density. We started with the hill and the ball, and then we went to this concept of reduced gravity and buoyancy. So let's now go into a fluid parcel that has got a vertical profile of density like this. Obviously heavier density at the bottom and lighter density at the top. And let's take two fluid parcels and displace them from their position to new positions. So rho 1 and rho 2 with these densities are over this profile of density rho z, which is varying in this way. So we are going to move rho 1 up to z2 where rho 2 was, and we're going to move rho 2 down to z1 where rho 1 was, and z2 is obviously z1 plus some delta z. We keep carrying these delta z because we can easily convert them into partial differential equations when delta z is small enough, right? We cannot do those when delta z is huge, if you remember your basic theories of how we derive derivatives and partial differential equations and so on. So what is the main thing to remember here? That if the system is in hydrostatic balance, then when rho 1 comes up here, it has to have the same pressure when rho 2 as the environment at z2. And if rho 2 comes down to z1, it has to have the same pressure as the environment at z1, because the pressure at z2 is equal to the weight of the air column above it or fluid above it, and at z1 it's the fluid weight of the fluid, mass of the fluid above it, right? Very simple concept, but we must always remember that. Then we will make a simple assumption before we go to the atmosphere. Ocean is heavily dependent, ocean water's density is heavily dependent on temperature. Of course, we will see later on that it's also dependent on salinity. But to make a distinction from the atmosphere, we here go into a lab where there is no salinity, just fresh water. And air is complicated because it's compressible as opposed to water, which is not compressible. So air density is going to be dependent on pressure and temperature, right? Rho P equals rho RT, remember? So the density rho at any point is going to depend on the temperature, whether you warm it or cool it, and that is related to the reference density, some density at a particular temperature that's chosen as a reference temperature, and it's going to depend on the thermal expansion coefficient. Okay, in the ocean it turns out that the pressure increases so much that the thermal expansion coefficient itself has a temperature dependence, but nonetheless in the laboratory where we will do this, the water container, the water table, water tank we are using is not that deep. Okay, pressure is not a big impact. So the temperature relation is going to look like this: rho ref times 1 minus alpha T minus T ref. Alpha is positive, so if you warm the temperature, you're going to reduce the density. If you cool the temperature, you're going to increase the density within reasonable limits, right? So rho E again is the environment. So we are always talking about a parcel and the environment. Why? Because as we said, if we move this up here, you have to replace it with something else for mass continuity, so the fluid has to adjust. So environment at rho z2 has density of rho 1 plus d rho dz times delta z. Delta z is this height. Very simple relation. So the environmental density here is lower than the environmental density here because d rho dz is negative, so density decreases as you go up, as we see in this figure. So let's go back to our buoyancy, which is minus g times rho p minus rho e divided by rho p. So at z1, b is g over rho 1 times d rho dz. So this we can replace with d rho dz because d rho dz times delta z is this density difference. I'm not rushing through this, but I think you can easily see. You can just think that if you write this as delta rho divided by delta z times delta z, then delta z would cancel. But in a continuum, because this is a continuum, we are going to write it as d rho dz times delta z, because the density variation, density profile is continuous, right? So now we take this simple situation and we want to see when is the displacement of the fluid in a stable situation or an unstable situation. Okay, so we can create obviously see whether the parcel at at z1 is positively buoyant, neutrally buoyant, or negatively buoyant. Obviously that's going to depend on d rho dz of the environment at z1, right? So if d rho dz is greater than 0, it's going to be positively buoyant, which means if you move it, it'll continue to move in that direction. Neutrally buoyant means if you move it, it'll come back. Oftentimes we will see that it'll overshoot the position and has to come back, so you create these oscillations which are related to gravity, and we call them gravity waves, as we will see later. And if d rho dz is a negative, then it is negatively buoyant. So if you displace it, it will keep going in the opposite direction as positively buoyant situation. Okay, so to think in terms of temperature, remember density is not a great variable because we cannot measure it directly, but we can always measure temperature very easily. So if you plug in the density relation with temperature and replace d rho dz, then you're going to get dt dz. So it flips sign here, you have to be just careful. It was positive equal negative, whereas for density, for temperature, it's going to be negative equal positive. Okay, so if temperature gradient is negative, as it is in the troposphere, then the system is unstable. Instead of saying buoyant and negatively buoyant and positively buoyant, we are going to say stable and unstable. Unstable means it'll keep on moving in the same direction if you perturb it. Stable means it'll come back. Okay, so unstable if dt dz is less than 0, as it is in the atmosphere. Neutrally stable if the temperature gradient is 0, so you can keep on moving it to a new position, nothing happens because temperature doesn't change. Whereas if dt dz increases, of the environment increases with height, let's say with z, then it'll be stable. So we'll see that we will do dry and moist convection and see that dry convection is always stable in the atmosphere, whereas moist convection tends to be conditionally stable, as we will see. Okay, so you can see how we are building the concepts towards convection in the atmosphere, which is an important concept. We obviously in the models, convection is a very complicated issue. Lots of parameterizations because there are molecular level processes involved all the way to the cloud scales, many orders of magnitude, and we don't understand the processes from first principles, so we end up representing them empirically based on observations of relations between temperature, stability, humidity, and density, and vertical motion, and so on and so forth.